Hi everyone, today we're going to study uses of matrices in graphics. Computer graphics is a computing field that involves the creating, storing, and processing of image content via computer. Digital images are referred to as matrices when used in graphic design. The rows and columns of the matrix are equivalent to the rows and columns of pixels. Also, the number entries match the color codes of the pixels. Additionally, graphs can be represented using matrices. Each column and row of a matrix is a point on a network, and the value of their intersection is the link they have. Hence, every graph can be represented as a matrix. The fundamental part of computer graphics are geometric transformations that can change the position, size, orientation, and shape of an object. Let us study linear transformation in 2D. Consider the point x equals the column matrix xy, vector capital V equals the column matrix with elements t sub x, t sub y respectively, and transformation matrix capital T equals the 2 by 2 matrix AB, CD respectively. The following transformations can be defined. Number 1, translation. Rotation. Third, reflection. Number 4, scaling. Number 5, shearing. Let us study translation. We have here point T with coordinates xy. We're going to translate this into this point T prime with coordinates x prime, comma, y prime. The translation of a point capital X equals the column matrix xy, vector capital V equals the column matrix T sub x, T sub y respectively is given by, and this is the column matrix x prime, y prime respectively. This is equal to matrix X plus matrix V. When we substitute the corresponding values or the corresponding matrices, it will be like this. Doing the operation, we will have this column matrix. The first element, x plus t sub x. The second element, y plus t sub y. Next is rotation. We have here point T, and we are going to rotate this into another point T prime to be rotated at an angle theta. The rotation of a point capital X equals the column matrix xy by an angle theta by the transformation matrix capital T equals the 2 by 2 matrix cosine theta, negative sine theta, cosine theta respectively is given by, this is the new point x prime, y prime respectively. This is equal to t times x. When we substitute the corresponding matrices, it will be like this. When we simplify this, we will have our new column matrix. The first element, x cosine theta minus y sine theta. The next element will be x sine theta plus y cosine theta. Let us study scaling. Suppose we have here one square, and we are going to scale this into this bigger square. The scaling of a point X equals the column matrix xy by the transformation matrix T equals the 2 by 2 matrix. Elements are alpha, 0, 0, beta respectively, is given by our new point x prime, y prime respectively. And this is equal to capital T times capital X. We substitute the corresponding matrices, it will be like this. And our new matrix is a column matrix with elements alpha times x, then the second element beta times y. Let us now discuss reflection. Reflection is a special case of a scaling where the size of the object does not change. For example, we have one picture in the first quadrant. This is the original picture. The reflection of this picture in the second quadrant will be like this. The reflection of this original picture in the third quadrant is like this. And the reflection of this original picture in the fourth quadrant will be like this. The reflection of a point X equals the column matrix xy in the x-axis by the transformation matrix T equals the 2 by 2 matrix 1, 0, 0, negative 1 respectively, is given by our new point x prime, y prime respectively. This is equal to capital T times capital X. Substituting our matrices, we will have like this. And the new matrix will be the column matrix with elements x, negative y, respectively. The reflection of a point X equals the column matrix xy in the y-axis by the transformation matrix T equals the 2 by 2 matrix with elements negative 1, 0, 0, 1 is given by the new point x prime, y prime respectively. This is equal to capital T times capital X. We substitute the corresponding matrices, it will be like this. And the new column matrix is equal to negative x, positive y, respectively. The reflection of a point X in the column matrix xy in the y equals x axis by the transformation matrix T equals 0, 1, 1, 0 is given by the new point x prime, y prime respectively. This is equal to capital T times capital X. Let us substitute the corresponding matrices, it will be like this. And when we simplify, our new point will be this column matrix yx respectively. The reflection of a point X equals the column matrix xy in the y equals negative x axis by the transformation matrix T equals the 2 by 2 matrix 0, negative 1, negative 1, 0 is given by the new point and column matrix x prime, y prime respectively. This is equal to capital T times capital X. When we substitute the corresponding matrices, it will be like this. And when we evaluate the product, we will have negative y, negative x, respectively. Let us now study shearing. Skewing the object with respect to the x or y axis is called shear transformation. The shearing of a point X equals the column matrix xy by the angle alpha with respect to the x-axis and by the angle beta with respect to the y-axis by the transformation matrix T equals the 2 by 2 matrix 0 tangent alpha tangent beta 0 is given by this new point. X prime, y prime is equal to capital T times capital X. We substitute the corresponding values, we will have like this. Evaluating the product of the matrices, the new point will be y tangent beta, x tangent alpha, respectively. Please refer to this picture for the shearing process. Hi everyone, today we're going to study uses of matrices in encryption. A very common use of matrix in daily life is during encryption. We use matrices to scramble data for security purposes and to encode and decode data. There is a key that helps encode and decode data, which is generated by matrices. Let us now discuss encryption. If capital P is the plain text matrix and capital K is the encryption key, then encryption rule is given by K times P mod 26. Note that A mod 26 is the remainder when A is divided by 26. Let us see some examples. This is the first one, 15 mod 26. We can see here that 15 is less than 26. In this case, if we divide 15 by 26, the answer is 0 and the remainder will be that same value, 15. So the answer here is 15. By this example, we conclude that when the letter A or the number A here is less than 26, that value is the answer for this mod. Another example, 52 mod 26. When we divide 52 by 26, the answer is 2 and the remainder is 0. It means this 52 is divisible by 26. So the answer here is 0. Another example, 114 mod 26. When we divide 114 by 26, the quotient is 4 and remainder is 10. So we write here the remainder 10. Let's see example 1. Encrypt the plain text help using Hill cipher for the given key capital K equals this 2 by 2 matrix 3, 3, 2, 5 elements respectively. So the key here is a 2 by 2 matrix. Thus, we divide the text letters by 2's. Meaning, the word help is now separated by first group is HE, another group is LP. Then we write here the formula for the encryption. K times P mod 26. Let's begin with identifying the P value for the two groups of letters. Let's start with the HE, and we write here as a column matrix HE respectively. Then we will write numerical value for the letters H and E. First, let us write all the letters of the alphabet. Then we will assign values for them. Take note that the first letter A has the value 0, followed by 1 for B, 2 for C, and so on. The last number must be 25 for the Z. So the value for H is 7 and the value for E is 4 respectively. So we have now our matrix 7, 4. It will be same for the LP. First, we write it as column matrix, and then we write the corresponding number for the letters. 11 for L, 15 for P. Next row will be for the KP. It means our encryption key given here, 2 by 2 matrix, to be multiplied by the corresponding P value for the two groups. We're going to multiply this 3, 3, 2, 5 by the matrix 7, 4. So that will be 3 times 7 plus 3 times 4 equals 33. Then 2 times 7 plus 5 times 4 equals 34. For the LP, the KP will be 3 times 11 plus 3 times 15, and that is 78. Next, 2 times 11 plus 5 times 15, and that is 97. Next step will be to write now the KP mod 26. For this 33, 34, we will write like this. 33 mod 26 equals 7. 34 mod 26 equals 8. Remember that the mod here is the remainder when we divide this 33 and 34 by 26 respectively. So the remainders 7, 8 we will write in here. After that, we're going to return back the alphabet value for 7 and 8. 7 will be H and 8 is I. We will do the same for the KP of LP. So we have 78 mod 26 equals 0, 97 mod 26 equals 19. And we write this 0 and 19 as column matrix. We return back the alphabet value for these numbers. 0 is for the A and 19 is for T. So the ciphertext will be HI for HE, then AT for LP. We'll just put them together and the final answer is this, HIAT. Example 2. Encrypt the plain text attack using Hill cipher for the given key capital K equals the 2 by 2 matrix 1, 2, 3, 4, respectively. The key here is given as 2 by 2 matrix. Thus, we divide the text letters by 2's. So the word attack is now divided into 3 groups: AT, TA, and CK. Then we write here the formula K times P mod 26. Let's begin with identifying the P value for the 3 groups. Let's begin with AT, and that will be, first we write as column matrix, then we write the corresponding numerical value for the letters using this table. So we will have here 0, 19. For the TA, first we write as column matrix TA, and the numerical value will be 1940, 0 for A. For the CK, the column matrix is here, and the numerical value will be 2 for C, 10 for K. Then let us do the KP. We multiply the key by the P. The 2 by 2 matrix 1, 2, 3, 4 will be multiplied by the P of these 3 groups respectively. Let's begin with AT, which means this 1, 2, 3, 4 matrix multiplied by 0 and 19 matrix. So we will have this 1 times 0 plus 2 times 19. We get 38. Then 3 times 0 plus 4 times 19. We get 76. Next, for the TA, 1, 2, 3, 4 matrix multiplied by 19, 0 matrix. So we will have 1 times 19 plus 2 times 0, we get 19. Then 3 times 19 plus 4 times 0, we will get this 57. For the CK, we will have this matrix 1, 2, 3, 4 times the matrix 2, 10. So we have 1 times 2 plus 2 times 10. We will get this 22. Then 3 times 2 plus 4 times 10. And the answer is 46. Next row will be the KP mod 26. Let's begin with this 38, 76 matrix. So we write here 38 mod 26 equals 12, 76 mod 26 equals 24. These are the remainders when the numbers 38 and 76 are divided by 26. So these numbers we will write here, and then we will return the alphabet value for the two numbers. The letter M for 12, the letter Y for 24. Then we go to this matrix 19 and 57. So we write here 19 mod 26 equals 19, 57 mod 26 equals 5. The values 19 and 5 we write as column matrix. Then we return the alphabet value for 19 and 5 respectively. And these are T for 19, F for 5. Then the KP mod 26 for this 22, 46 matrix. We write here 22 mod 26 equals 22, 46 mod 26 equals 20. These numbers 22 and 20 we will write as column matrix. Then we return the alphabet value for the numbers respectively. The letter W for 22 and letter U for 20. So the cipher text will be MY TF W, U. Just put together the three groups and we have this M, Y, T, F, W, U. This is the final answer. I hope you learned something from this video. See you again next time.